Good morning. The title of this presentation is Predicting Unconventional Shale Reservoir Properties from Seismic and Well Data using Convolutional Neural Networks. Our goal is to predict rock properties suitable for unconventional reservoirs, such as this estimate of the brittleness index or the volume of quartz. Throughout the talk, we'll show our estimates along this arbitrary line where we compare the predicted values from the convolutional neural network versus the actual measured values at the well control. The elastic and rock properties can be estimated both by theory-based approaches such as seismic inversion, as we show on the top here where we're estimating the P impedance from pre-stack inversion, or data science-based approaches where we're using deep neural networks to also estimate the P impedance, but this time using a convolutional neural network. So why are companies interested in DNNs? Well, first, the ability to generate high-resolution 3D reservoir images. You can see that we're accurately resolving very thin layers and also with a higher degree of accuracy using the CNN. There's the ability to directly predict reservoir properties. So in the previous example, we were able to create a mapping that went from the seismic data directly to the volume of quartz. The ability to quickly update the prediction as new data, for example, well control becomes available, and the ability to transfer learnings to adjacent 3D seismic surveys. And this all and then there's the potential of artificial intelligence to reduce project time, expertise, and cost. The convolutional neural networks used in this talk are forms of supervised learning, where we try to find a relationship between the target log, for example, the volume of quartz, and the seismic, here represented by different seismic attributes. So we've tried to find this relationship at the well control, and then using the seismic, predict target logs or the target property away from the well control. Any log can serve as the target log. So here they're predicting porosity, the shale content, and the water saturation. But in order to do that, you need a variety of different porosity values in order to train the neural network. Same thing here, need a variety of different clay values and also need a variety of different water saturation values, and ideally combinations of all these different parameters. And this is often the limiting factor in performing the analysis, is often with a limited amount of well control, you don't have enough data to adequately train the neural network. Our solution to this is to train the convolutional neural network on synthetic data. We generate this from nearby wells. First, we calculate the statistics of these wells, and this will be used later for the simulations. And then we also choose and calibrate a rock physics model. The rock physics model is used to predict situations not sampled by the original well control. So for example, we could model how the porosity influences the elastic parameters and then ultimately the seismic response. So we use the statistics in the rock physics model to generate many synthetic wells, and then for each well we generate synthetic gathers using a convolutional modeling scheme and the Zopert's equations. We then train the CNN on the synthetic wells and synthetic seismic gathers, and then having determined the operator, we then apply that to the real seismic data. We'll first introduce the Barnett Shale example and the methodology will follow, then how we're generating the synthetic data, then review convolutional neural networks and how we're adapting them to predict reservoir properties, and then show results on this Barnett Shale data set, and then summarize. So the Barnett Shale data set we'll show is from the Fort Worth Basin, Texas. Success requires identifying brittle, frackable, productive layers with high quartz content, which in turn requires reliable elastic property volumes. In addition, we'll estimate effective porosity, clay, quartz, and Kerogen volumes. We'll generate the synthetic data following our 2021 TLE paper. The key difference is that we use the Key and Zhu 2000 rock physics model appropriate for unconventional reservoirs. The resulting synthetic data are used to train the convolutional neural networks to estimate first the elastic properties, from which we also will then generate the brittleness. Key to doing this is using transfer learning to incorporate the real data, and we'll see that makes a significant improvement on the results. The second thing is that we're going to predict the porosity, quartz, Kerogen, and clay volumes with a second convolutional neural network. And then when we compare this quartz volumes to the brittleness as the ultimate interpretation display. We can compare these rock property estimates with more traditional data science-based approaches using hand-picked attributes and multilinear regression. And we'll see that the convolutional neural network predicts the reservoir with much higher frequency and also with better well ties. Let's now talk about the synthetic catalog workflow. The first step is to perform a petrophysical analysis to generate the input for the rock physics model. Next, we need to pick a rock physics model appropriate for unconventional reservoirs. In our case, we're going to use the Keys and Zhu effective media model. This model models both the P wave velocity as a function of porosity and the S wave velocity as a function of porosity. But just as importantly, you can see that the aspect ratio also controls the fit. So when we calibrate this model, essentially we look at the data, we perform an inversion, and we're going to determine the aspect ratio of the original data. And we'll use this as one of the additional petrophysical curves when we generate when we perform the forward modeling. Next, we perform a statistical analysis. We break the well log up into a series of different lithofacies, and for each lithofacies, we determine the trend and the covariance matrix, and we'll draw our sample statistics from these lithofacies dependent statistics. Next, we do the simulations. So the first step in doing the simulations is that we generate petrophysical curves based on the statistics of the original wells. But in addition, we systematically vary the key parameters of the reservoir layers by perturbing such parameters as the porosity and varying it so we increase the decrease the porosity or increase the porosity. We also change the thickness. We'll also change the Kerogen volume and also the clay volume. And by doing this, we can sample all the different situations we might expect that the reservoir might encounter and provide training data for all these different situations. So we generated 189 pseudo wells. We first generate the petrophysical curves, and then using the rock physics relationship, we then generated the elastic curves. So this just shows how we've a subset of this where we've varied the porosity, and then along with the other petrophysical curves, we calculate the P velocity, the S velocity, and the density. And then we go ahead and for each one of those pseudo wells, we generate synthetic gathers using a convolutional modeling scheme and the Zopert's equations. So next, let's talk about the convolutional neural networks. And the convolutional neural network we're using is based on those used for image recognition, where you provide a picture and you try and identify what that particular picture actually is. The input consists of 3 channels, red, green, and blue, and it goes through 2 steps, convolution and then pooling. So we'll have a 2D convolutional filter, and associated with each 2D convolutional filter will be a feature map, or you can think of it like a seismic attribute. And then it will go through a pooling layer, which is a form of nonlinear downsampling, so it's reducing the size of the data. Then another layer of convolutional filters. Then you go through another layer of pooling. We flatten the resulting images, and then this is fed into a fully connected neural network. And then associated with each one of these outputs here is a probability, and you choose the category with the highest probability. Now we can also output continuous variables here, and that's what we'll do in our particular case. So rather than providing an image, or an image of a boat or cats, we're going to bring in seismic gathers, and we're going to construct a seismic image associated with this. So we have data from 4 to 42 degrees in 2-degree increments. So we'll have a 20 by 20 pixel image, and associated with this will be one porosity value for this particular well. And we'll just extract a series of different images by running a sliding window, and associated with each one of these images will be a particular target variable. And once again, we go through this network. We have a convolution, 2D convolution, pooling, 2D convolution, pooling, and then we go into the fully connected neural network. And we train this network once again just by doing backpropagation, and we come up with optimal attributes or features that feed in that will predict this particular property. Now, since we're doing backpropagation, we can automatically determine these features. We can predict multiple targets simultaneously, and so this greatly reduces the amount of effort compared to a traditional neural network, where you have to select attributes particular to each one of the targets you're looking at. So here's an estimate of the P impedance using this convolutional neural network, and then we're comparing it to that of deterministic inversion. And both of them are doing a pretty good job, with one exception. In this area here, you can see that we have some very high impedance or violet values, and the actual log in this area are red values or intermediate values. And so we're not doing a very good job here, nor are we doing a very good job here. The convolutional net's doing a little bit better over here. And the reason that we're having a problem here, it becomes apparent when you look at the near angle stack versus the synthetic data. When we actually look at the zone of interest, you can see that there's a poor tie between the synthetic data and the actual seismic data. And the problem might be due to the wavelet, or maybe it's multiples, but there's a poor tie here. And because the post-stack inversion, or let's say the pre-stack inversion, has a convolutional model, and also our synthetic data, when we're training it, it also has a convolutional model embedded in it, we end up with problems in these particular areas because of the poor tie between the synthetic data and the actual seismic data. So what we'd like to do is to incorporate the real data into the training to allow for differences between the synthetic and the real data. And the way we do that is via transfer learning. We're first going to train the network as we did before. So we train it, and then we're going to hold the convolutional layers constant, or the weights associated with that. And then we're going to swap out and use the real seismic data and the real well logs here, and then update the weights associated with the fully connected neural network part of the network. And by doing that, we can improve the overall fit. So here's the updated P impedance as a result of the convolutional neural network with transfer learning. And what you can see here is that we've improved the fit. Like, we have intermediate values on the well log, and once again, the prediction here has intermediate values, whereas the old or the pre-stack conversion, we have very high values here. So obviously we've improved it here, and we've also improved it here. Plus are able to image some very thin layers here, which is also very which looks very good. So we can take our estimates of the P impedance, S impedance, and density, and then calculate other properties. So here we calculate the Poisson ratio and the Young's modulus, and we'll later on in the talk use this as the input to calculate brittleness. We did two convolutional neural networks, one for elastic properties, which we just showed, and secondly for reservoir properties such as the Kerogen, clay, and quartz volumes, as well as the effective porosity. The bottom shows the Kerogen volume predicted using a convolutional neural network. And for comparison, the top shows the same, but using multilinear regression, using a more traditional workflow based on seismic attributes as input. The wells are displayed in color. For display, the wells are filtered to 60 Hertz for the multilinear regression and to 100 Hertz for the convolutional neural network. These filters are chosen so as to optimize their respective displays. The CNN shows more detail, better lateral continuity, and appears less noisy. The next slide compares the multilinear prediction of the clay volume with the CNN on the bottom. Once again, you can see that the CNN ties the well control better and has more detail than the multilinear regression, in particular at the blind well control. For the effective porosity, probably the results here are much closer together. They're both quite good, but it's not as clear cut which one is actually better. And lastly, here's the volume of quartz volume, or the quartz fraction. And again, we're able to achieve really good high resolution estimates with good lateral continuity. We'll compare this last estimate, that of the quartz volume, with the brittleness, and we calculate the brittleness following Rickman, where we first calculate a brittleness due to the Poisson ratio, and it's essentially just normalizing the Poisson ratio, normalizing the Young's modulus to calculate a brittleness value, and then averaging the two of these in order to calculate the brittleness. So the top shows the brittleness, the bottom shows the volume of quartz, and areas with higher values, that is the reds or the deeper blues, would be the better areas in determining where to drill. So in this talk, we've shown that CNNs can accurately estimate unconventional reservoir properties, including effective porosity, quartz, Kerogen, and clay volumes. I think we've shown that the CNN estimates better resolve the reservoir and blind well control compared to the traditional multilinear regression type of approach, and that the fact that the CNN can simultaneously predict reservoir properties lead to significant efficiencies. When we did the multilinear regression, you have to pick attributes specific to each target, so it takes at least 4 times as long in order to do this, plus more expertise in terms of running the workflow. Key to performing this work was generating a well-sampled synthetic training data set using the Keys and Zhu RPM. And the synthetic modeling is similar to what an interpreter might do to understand the seismic response due to different reservoir conditions. For instance, if you do a tuning study or look at how fluids influence things. And lastly, the transfer learning was key to getting better results, and we did this by incorporating the real data into the training via the transfer learning. So I'd like to thank Alfonso Marini and Roberto Lotti for their feedback, and also some of my GeoSoftware colleagues. So thank you.